Hey there, how you doing? Welcome to the channel. So I think today's Saturday. It's really a beautiful day out there. San Diego. Yeah, so I was kind of working on the power supplies for my clock project, and so I figured it's a very incomplete kind of thing, but I figured I would just kind of go over the initial thoughts on what I was thinking for power supplies. So we'll go ahead and get into that. So let's stop this. Let's go and share. So what I want to do is I'll just really quickly, I had talked about this in my last video, but right here, let's see. Okay, so basically the idea is we have this clock and we're going to have this long time countdown and stuff. We're going to use these IV actually 11 tubes. I need to update that. But, you know, at first guess, we're going to have a total of 12 tubes, IV 11 tubes for the years, months, dates, for the countdown, etc. I mean, we could count up too, but and then you have your clock function in there. So that's kind of what we're dealing with. Okay, so so going back to the, let's see what I want to show. Oh yeah, this one here. So I want to show here. So basically what we're going to have over here is on the left, you're seeing here we have the PIC microcontroller connected to the PC. And I talked about this in my last episode, how, you know, I really want to put some opto isolators in here, or optocouplers, and really want to make sure that we separate the power domains, because this PIC microcontroller is running off the USB power, which is on the PC. And, you know, really, I don't want to connect that ground to this ground over here. This has to, on the right, the supplies for the logic chips, and especially the VFD tubes, requires, you know, somewhere between 15 and 30 volts on the anode and grids, higher voltage. And so I want to isolate them. So today what I want to talk about is just the preliminary calculations. I'm trying to figure out, like, how much of a power supply do I need over here? And what voltages do I need? So if we go over here, basically right now I'm using a wall wart that, hey, basically, it's so funny, I struggle to pronounce that, wall wart. Terrible with W's, terrible. But basically right now I have one that's actually producing 15 volts or 12 volts, something like that. And it's able to deliver over an amp at that 12 volts. So that's pretty good. But conceptually, you know, I'd like to be a little bit flexible. I know there's a lot of 9 volt, wall plugs out there that you could use. Now, when I check this, it's very interesting. It's actually pretty well regulated, not regulated, but pretty well smoothed. Like the power, there's very low ripple on it. So I was kind of impressed. That means they have a rectifier in there. And sometimes, you know, when they have these rectifiers, they don't really rectify them. They don't smooth them out. But this thing must have, the particular one I'm using right now has a particular beefy power supply in there, because beefy capacitor in there that's filtering it, because it's pretty well regulated. But going back to the power supplies, what we have here is, you know, we need this high voltage supply, and I'm saying 15 to 30 volts because I don't know what it's going to be yet. Because basically what I'm going to do, I'm going to take the tubes and I'm going to vary the voltages. And so I have the voltages on the anodes and the grids that can be anywhere between 15 and 30 volts. And then also have this cathode supply, which I have right now at 1.5 volts, but it can be a little higher to 1.65 volts. So what I have to do is I'm going to play with those. When I get this set up, I'm going to play with the voltages, try to find the best combination. Like, if possible, you know, a lower voltage is better on this high supply. So if I can get away with 15 volts without looking really dim or crappy, then, you know, I'll go with 15 volts. So that one's kind of TBDs, but I know that I need a high voltage supply, and I know that it needs to be higher generally than my input voltage. So if my input voltage is coming in at 9 to 15, well, if it's 15, then it's okay, but I have no drop, and I'm not using ULDOs or LDOs. So an LDO would be a low drop regulator. So I don't really have that option. I mean, generally, I'm assuming that it'll be at 20 volts or whatever. So this is going to be a boost regulator module. But the question really is, you have to figure out like how much current do you need out here on this side? You know, how much current? This is a critical thing because it determines how you design this supply. Like in reality, what's going to happen here, if I need like 2 amps of current at 30 volts, I'm not going to get it from one supply. So, you know, I'm just trying to get an estimate, an idea of like how much I need. Then I have the logic chips. Over here, we're using HC shift registers, the 595s, which are HC CMOS logic. You know, they require 5 volts and they require current too. Got to figure out, hey, how big does that supply need to be? And then also here for the cathode, the 1.5 volts, you need to figure out how big that needs to be. So now what we'll do, we'll go over there and we'll share some more calculations. We'll go to my, this guy over here, and we'll share this. Yeah, so what I'm doing over here, you know, for example, back here, I had shown this before. I was using a 317T variable regulator and did the calculations. And fortunately, I was able to get the 1.5 to work. And it's really interesting because, you know, they talk here about how they recommend that you have, you know, something like it has to be driving a minimum load current is greater than 10 milliamps. And I found this out because I'm looking at it and I had no load current and I was looking at it as 2.65 volts. So first, of course, I'm thinking, oh no, I screwed up the circuit. I got the resistors wrong. And sure enough, I put a load on there of like 50 millivolts. It's like, oh yeah, it goes right to 1.5 volts. So that's one of the things that you have to kind of be careful, especially these kind of circuits. These are old. These are like really old circuits. These are not modern. Like in modern, like when I work in, you know, the lab and real stuff, we have these supplies. Like if I set it to 1.5 or 2 volts, I can have 0 load. I can drop a large load on it. It doesn't matter. It will just handle it. But with these old circuits and these simple circuits that I'm making, you know, you do have to kind of follow that kind of, if they want some current coming out, because if they don't have any current, they're not going to be regulated. So I learned that one. But so let's go to the power. Okay. So what I'm going to do is I'm going to try to zoom in over here on these calculations. So what I did is I'm trying to do it kind of per function in VFD. So we have a tube, an IV11, and we have the cathode current, and I'll call this VC. This voltage, as I said, 1.5 to 1.65 volts. And then I go to the data sheet. When I looked at the data sheet, and I'll show you that a little bit, maybe I should share that now. Let me just show you, because this is great. I learned this from someone else. Let's stop share. And what we're going to do over here, yeah, this one here. Okay, we're going to share here. And I'm going to look at this guy. So they have this translated IV11 VFD2 pin sheet. I'm sorry, data sheet. So they have some estimates here, okay? And so we see that pins, you know, here they have the pin out and they have the display. And, you know, it's funny, they don't tell you which, you know, pin 3, 4, 3 through 10, which one lights which segment. So I guess you have to guess at it. Or it's possible that I think what they're doing is it's like a standard, the 7-segment display, but, you know, we'll see on that. So pins 1 to 11 cathode. So this supply is our 1.5 volts. Okay, that's fine. And then 2 is our grid. That's this guy here. So the grid is controlling, you know, the voltage on that is helping control the flow of electrons somehow in there. And then you have your anodes, which, you know, you light the anodes for the segments that you want. So you apply a voltage to it. So now we look at the specs. So we have the cathode voltage here, 1.5 volts, anode 25 volts. And now this is what we get, working cathode current. So basically for the cathode, I'm going to assume a worst case 110 milliamps going through the cathode. Okay, so fortunately, I only have one of those and it's at 1.5 volts. So that tells you per each tube, the power supply for the 1.5 for each tube, I need to have 100 plus or minus 10. We did over-design power supplies, over-design, use larger resistance, over-design power supplies, always, right? So we're going to use 110 milliamps. That's what we're going to assume. Working anode current, 3.5 to 5 milliamps. Okay, so we have all these anodes. So here we have 3 through 10. So we have 8 of them, 8 anodes. So we're going to go there, and of course, we're going to assume that it's going to draw 5 milliamps, the worst. And then the grid, it's interesting, the grid draws more at 17 milliamps. So basically, we can take these currents and we can use those to plug into our power calculations and try to figure that out. So this stuff is... this is the key behind this. It's so funny because I really struggle. I try to learn a little more about radios, and I'll look for like schematics for 20 meter, 40 meter, 80 meter band, old style direct down convert receivers and stuff. And the schematic has very limited information. There's not a lot of information there. It's like, yeah, you have a value for a resistor, capacitor, coil. Especially coils are every piece of wire connecting it is an inductor and also a resistor, but like an inductor, and especially at these frequencies, like if you don't have the calculations that support it, it creates a lot of confusion because you don't really know. I mean, you look at the schematic and you have to reverse engineer, like, well, why did you use this value? And then you may have used the value because, whoa, we have 100 ohm resistance in this antenna that I told you, and I didn't really specify what it was, and blah, blah, blah. So that's why I'm trying to show like a little bit of the calculations behind it, here. So here we go. This is IV11. Here's the cathode. So once again, 1.5 volts. I'm going to label this the VC supply, 110 milliamps. So what I'm going to do is I'm going to do this is for one tube. And then what I'm going to do is so basically, well, actually, here up here at top, I'm just going to specify the function, what the function requires. So no, for one tube. I'm sorry, I'm doing for one tube. Yes, for one tube up here. So basically I have one cathode, so 1 times 110, so a total 110 milliamps. And then over here now we have the grid and the anode. Now both of these are going to run on the same supply, this 15 to 30 volt supply. I call it VH. So we have 17 milliamps for the one grid, but notice we have 17 altogether, and then the 5 milliamps for the anodes, but we have 8 of those. And I'm just going to assume that I'm lighting all the segments. So altogether we get 40 milliamps there. Now we have this SN74595 shift register. So once again, this is VCC. This is a different voltage. This is 5 volts, and this is going to be like standard 5 volt logic supply. Here I'm way overestimating most likely, but I'm estimating 10 milliamps per. In power, the equation for power is just voltage times current, okay? So that's what I'm trying to do here. Voltage times current will give you power, actually, but right here, I'm just trying to get the total amount of current. So, okay, well, I'm sorry. I got off track there. I'm not interested in power right now. I'm just interested in current, because the way it works is like if you buy a power supply, and like these modules over here, they'll tell you like, hey, it's a 1 amp power supply, and they'll give you the voltage. But the current is going to be affected by the voltage and all these other things. So you got to figure out how much current you need to drive for each voltage. So that's what I'm trying to figure out. Now this UDN2981, this is that driver IC, but it's going to be at the high voltage again. And here I'm just throwing in some estimate. Now we have 9 pins that are going to go through there at 10 milliamps for 90 milliamps. And I highlight that I really don't know. I have to understand better how to calculate power of actual transistors. And I'm not a transistor guy, so I don't. So that's something to be learned. And then I have this PC417. These are the optocouplers. And I know I'm going to have 4 of these. And these are not per tube. These are just 4 generic optocouplers that bridge the gap between the microprocessor and the actual logic. So I just have 4, only one case, 160 milliamps there. Okay, now we get here on line 8. Here's what I'm trying to say here. Per VFT tube, so for each tube, I'm going to have a 2981 and a 595. So you can see that I'm going to take lines 5 and 9. I'm going to have one of each of these included with each tube. Now, so for the 30 volt supply, how much current do I get? Well, For each tube, I have a grid in all the anodes. So I'm going to sum those up. So you see there, I've got 17 plus 40. So I've calculated for each tube, I'm going to have that much current, right? So it's 147 milliamps. Then for the 5 volt, here's where I'm adding this in. So I'm saying, hey, look, it's going to be the 595. And this PC, oh, I did that wrong. Look at that. I did that wrong. That is incorrect. So what I'm really saying, it's the 595 plus the 298, which is this guy here. That is my estimate, 190, and these are all in milliamps. So that's thousandths of an amp. Okay, 110 milliamps is 0.110 amps. Okay, and then the 1.5 volt supply. Here we go. We look. Is this F2 because it's 1 per tube, so it's 110 millivolts. Okay, so now this is per tube. So now we kind of just go, and once again, we just repeat our supplies like, okay, 30 volt, 5 volt, 1.5. But now I'm saying I want 12 tubes. That's the current plan. So let's see what's going on. So what I should be able to do is take my 147 milliamps times the number of tubes, and that's going to give me the total current. And I do that for all these guys, and I'm just going to check them right here. I'm looking up. So basically, when you do this in Excel, you can click on this. You have an equals that indicates an equation. The dollars lock the different things. So you're locking column before the letter. You're locking row, right? So that means when you copy it, if I drag this and copy this formula, the F10 will move, but the E12 won't. So basically, let's just look at this really quick. So I'm getting 2.2 amps. Now we're getting into amps. And then at the 1.5 supply times 12, 110 milli times 12. Okay, 1.3 amps. So now, and then what I did over here is I just tried to do an estimate of power. Now, this is messed up. This is not right. I'm really not buying that it's taking 52 watts. So once again, power is what? Is voltage. So this is the 30 volt supply times the current. Now the current is in milliamps, so I have to times by 0.001 to convert that current to amps to get watts. So it's 52 watts. And then this guy is showing, geez, that's too much, 11 watts. And then this guy is showing, the best estimate, really, I think that the 5 volt is way over. It's no way it's going to be 11 watts of power. And even the 30 volt for the tubes, it's not going to be 52 watts. There's no bloody way. The only thing that's accurate is the 1.5. That makes sense. Now, taking that, like, let's take the 1.5, since that's the only one I think is reasonable. If I take my 1.3, I need 1.3 amps. Now, if I go back over my regulator and I say, okay, well, what can this supply generate? How much current can it generate? So if I look through this thing and they're not telling me here, so I have to go look at the data sheet for the 317T. I have to look at the data sheet for that and figure that out. But that's the starting point. And if you have no margin. So for example, if I can take a single circuit 317T and it can generate 1.5 amps, then it might work. It'd just be a single circuit. If I cannot do that, then I have to have multiple 317T circuits, right? I have to have multiple of these. Now, what I would suggest from my experience is like I would simplify it. I don't want to take the output of this guy and just connect it to the output of another guy. What I would do is I would fragment the circuit. I'd say, hey, look, I'm going to split it to 2 different supplies or 4 different supplies, whatever it's going to be. And what I'm going to do is I'm going to draw, take 1/4 of the circuit driven by one, another 1/4 driven by the other one. So that would be 3 tubes off this supply, the next 3 off that supply, et cetera, that type of a thing. So, and then for reference here, this wall, like the current one I'm using is a 12 volt, 1.2, but that's only 14 watts. And I just have an old Dell one. And so for a PC, it's a lot more. It can generate 89.7 watts, and that's power supplied. It's saying that when you look at that thing, it's saying, hey, I'll give you 19.5 volts and you can draw 4.6 amps at that. And that means it's giving you 89 watts of power. That's a lot of power. So there's some things going on here with this power. I'm not believing the 52 watts. I think that's extremely high. And I'm not believing the 11 watts. I think that's extremely high as well. So the problem is I don't completely know how to calculate the power. So I'm sort of using worst case power, which is not the case. So what I'm going to probably do is I'll probably have to take a chunk of the circuit. Let's do 2 tubes. That's what I'm thinking. I'll do 2 tubes, build a circuit, and what I'll do is I'll measure the current on the supplies, and I'll take that as an estimate to get an actual power number of what I need. But given that, I know that at 30 volts, it's not, I don't have a supply that's going to give me 1.7 volts. So I need multiples. And once again, so I'm going to split the circuit if I need 2, blah, blah, blah. And then for the 5 volt, once again, nothing's going to give me 2.2. Now the 5 volts, I'm going to go, instead of a 317T, I'm going to go with what's called a 7805 because I don't need resistors. It's a similar type of circuit. They have the 7805, 06, 08, 09, 012. And what it is, they just have all these fixed voltages. And what they do is they internally trim it somehow, and you don't need the resistors. It just automatically, you can put anywhere from, so at an 8 volt, you have to have the drop because it's not low drop. So you have to be like 3 volts above minimum on the input. But if you are, then it would just automatically give you the output. So at a 5 volt supply, if you put 8 volts in, you automatically get 5 out with no resistors. So that's kind of what I'll do for that. And they're really cheap, and there's a bunch of them. Okay, so now what I wanted to do is I wanted to just do a little calculation here on the 30 volt supply. These are coming from these modules. So let me just go and I will show you the modules. So I'm going to stop share again. And I'm going to go over here, and I want to go to this guy, I think. Let's see what that looks like. And I think I have this module up. No. Yes. Okay, this is the one. Okay, so basically what I have right now is I have these modules, and these modules have this chip on it, and this is the chip underneath. So this is stepping up the voltage. So you're going to have a frequency, because it's basically it's going to have a switcher in there, and it's the way kind of you would do it is you take a capacitor. If you switch the voltages, blah blah blah, you can pump that up. You pump it up and boost it up. Now it's saying that it's a 5 amp switching current boost. Well, let's go down into the details. There's of course limitations on this, and what they did here is really cool. What they did on this thing is they're providing output current. So if you look at all these charts, they're saying, hey, if your output is 12 volts, you go to this table. If it's 24, you go to this. And then over here, 36 and 48. And then what they have on the x-axis is the input voltage. So here you're going from anywhere from 5 to 11 volts. Notice how they always go 1 volt under the output. You see what I mean? Because you can put a 5 volt in to 11 volt in, and it's going to provide, and you're setting it to provide 12 volts output. But what this curve is going to give you the output in milliamps, how many milliamps it can drive. Now you see this changes. So if you look all the way here on the left, if you're only providing a 5 volt input, then it's saying here it'll provide 1000 milliamps or 1 amp at the 12 volts. But if your input is up to 10 volts, then you go to this part of the curve and it will provide you 1.5 amps. And likewise, you can go to the 24 volt and you have a similar curve, right? So you have a different, the shape is different, but basically what's happening is the lower your input voltage, the less output current it's going to provide. Okay, so let's stop the share here and let's go back to our, and this is something new that I learned. I didn't necessarily know this. But once again, the question is going to be, hey, if I want 1.7 amps at this 30 volts, how many of these regulators do I need? Do I need one for all the 12 tubes, or would I need a couple of them? So that's what I'm trying to figure out here. So let's go figure this out. So what I did is I took this, the curves over here. And so just as I showed you here, we have the curves. Wow, it's terrible over here. And so what I did is I said, I'm pretty sure that my voltage is going to be somewhere between 24 and 36 volts. I mean, I'm not going to go to 36 volts. I'm thinking I'm running at 30 volts or 24 volts. Somewhere in between is probably where it's going to be based on what I've read. Maybe it'll go lower. That's a good point. And maybe I should do the calculate. I don't have a 20-volt curve here, but I can interpolate that. So what I did is I just took from these charts, I looked these up. So what I did is I said, okay, for the 24-volt chart, I go to this chart over here in the right corner and I say, okay, and I'm saying that I want my input voltage values of 9, 12, and 15, right? So I'm the wall plug that you're sticking in there, I want it to have a couple different options from lower to higher voltage, right? And so now I go over here and I say, okay, at 9 volts, I'm on the 24-volt output. 9 volts, you go up here, it's going to be 800 milli. And then at 12 volts, they're going to give me about 1.2 milli. And then at 15 volts, you can see you go up here, it's 1.6. So I go to all the charts and I put this in. So you can see 1.8 blah. And then likewise, I go to the VOUT36 chart, okay? VOUT36 chart, and I get these numbers here. So what you see is happening as the voltage is getting higher, and it's the delta, right? So the delta here, because my output voltage is higher, but my input voltages are still low, we're getting less current out, okay? And this one was interpreted, so I'm being, what I said, a little pessimistic, okay? Because if I go, so VOUT36, 9 volts, so 36, 9 volts, okay? So I'm at the 36, this chart here, 9 volts, it's not there, but I can see that it's, 100 millivolts per volt on the input. So I can drop it and I'd say it'd be 500 millivolts at 1 volt lower at 9 volts. And so that's why I said 400, a little pessimistic. Now what I can do is just interpolate, right? Because I'm not interested in 36. I may be interested in 24, but I don't know. But I'm thinking, well, what if I want to be at 30? So I need to figure out what current can I get. So we just kind of a linear interpolation. We just say, hey, so for each point at 9 volts, I can take at the 24-volt case, hey, I get 0.8 plus 0.4 divided by 2. That's an estimate of what I should be able to get at 30 volts in between. And you notice that 30 minus 24 is 6 and 36 minus 30. So 30 is basically in the center between 24 and 36. So a simple linear interpolation should be good. And we do that for the other points with the 12 volt in, and we also do it with the 15 volt in. And so now we get these numbers. So now it's telling us that, like, hey, at 30 volts, if we're going to run at 30 volts, you're estimating that this thing will give us at a 9 volt input 0.6 amps, 12. Now going back, so we can see that I'm over here at 1.7 and the best case is 15 coming at 1.3. So what does that mean? Well, I need to have multiple modules. The question is how many? So what I did over here is I said, what is the minimum available output current? I is current in engineering, electrical. So I just take the min of these two values here, right? Okay. So what I'm trying to do here is I'm saying, look, yes, I'm going to have 3 voltage inputs. It could be 9 through 15. But I'm never going to put it output at 36. So I'm just going to ignore these numbers, right? I used these numbers from the charts to figure out an estimate of what it's going to be at 30 volts. That's what I used it for. But I'm not going to set that voltage to 36 volts. So the minimum available output current at each input voltage, remember these are input voltage 9, input voltage 12, input voltage 15. So all I do is I just take the min of those two values and you see you get 0.6. And then we go to 12 volts. The min of those two guys, blah, 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 is 1 amp, right? And so that's what we get. So now I say, well, the number of modules needed. So if I have a 9 to 15 supply, what I can do is I just use the minimum. And I say, hey, look, you have 1.76. So once again, this is milliamps, so I'm converting. So I take my 1,764, move the decimal place 3 places to the left. You just go boop, boop, boop. See, that's how we do it in engineering. Everything's in units of 3. Also in finance, it's always units of 3. That's what difference between $1 million, $1 billion, $1 trillion, the units of 3. We use that in engineering, they use it in finance. It's just kind of convenient. And we have names for them. We don't really have names for the other units like 10 to the minus 4, 10 to the minus 5, but we have 10 to the minus 6, we do, micro. 10 to the minus 3 is 3. So it's just a convenience thing. So once again, back to here, we have to convert it. So we basically multiply by 0.001 to get it to amps. And what that means is that's 1.7 amps. So if I'm going to have the full range, then I need almost 2.94 modules, which means I need 3 modules, right? I need 3. I can't have 2 more. I have to have an integer number. But if I get rid of the 9 volt and say, hey, I'm got to drive with a minimum 12 volt input, then I only do 1.7. So I save a module, only 2 modules. So that's kind of calculations that you could do to kind of figure out. And all this did, see, this is not, it's not in any way final at this point. This is just really get a basic idea of what's going on. And I think at this point, given my uncertainty, some of my power numbers I think are really uncertain on these things. And therefore, because I'm not buying 52 watts of power for that, I'm really not. So what I'm going to do, and I'm stalled right now because I'm struggling to get these PC417 optocoupler parts. So what I need to do is I don't want to blow up my board. So I'm a little bit stalled on that. Hopefully this week those will come in and I'll get those calculated. Because then what I can do is, what I'll do is I'll completely set up this circuit with 2 digits. And I'll have the optocouplers. I'll be able to hook this up and be able to experiment. And then I'll show the coding to basically control 2 digits. And what I'm going to do is I'll set up a test program. What the test program is going to do is just basically cycle through numbers. I'll just have this both digits counting so I can see what they look like. And then I'll make adjustments to the voltages, the grid voltages, the anode voltages, and then also this cathode voltage, and kind of decide, do I want to raise them up, lower them, and kind of make a decision based on what visually I see with the tubes. And then from there, I'll figure out if I can get an estimate of power. I don't, the problem is I have to measure current on the supplies, and there's ways to do it, but I need more chips and stuff. So I think that'll do it for this one. So yeah, so those are some of the considerations. I think that very often with this stuff, you know, if you're just doing these little projects, you don't have to pay too much attention to it, but, you know, I think it's, you know, probably healthy to try to do it, try to get an estimate, especially with these tubes, because these tubes, you know, if you, these are VFT, so VFD, vacuum fluorescent displays. So they're not as much, they're not as power hungry as Nixies. So if you were doing something with Nixies, you know, Nixies, you got to have much higher voltages. I mean, here I'm debating 15 to 30 volts. Nixie, I think that plate, you got to put it to 170 volts, something like that to get that to glow. Now, if you're at 170 volts and you still have a couple ohms in there, you know, what is that going to be? You're talking significant power. And so then if you're going to like make something with even a clock, you just have to kind of consider the power, you know, how much power you're going to need. So I think that does it for this one. So hopefully that kind of shows some of that, some of the issues that you need to think about, and also the, you know, the ad hoc nature of it. You know, I get a bunch of curves. So they're like, okay, here's your output. You set it here, give me a curve. And that's great. You know, it's not an exact equation. You just kind of estimate from it. And then we're going to apply our, like on a power supply for a project like this, a 2x factor means if I estimate and calculate that, okay, I need an amp, then I'm going to design and plan for 2 amps. So that way I don't have to worry about the problem. The thing is on a power supply, if you fall short, because we're not professional power supply designers, and some of these chips have current limiting and stuff like that, you have to understand when you run out, there's a couple things that happen. First of all, when you're at, you know, we're going to have to deal with heat sinks and stuff. I mean, you're sending an amp at 5 volts. You probably need a heat sink on that chip. And that's where you look at these packages or TO220s, because you're supposed to put a hunk of metal on that, right? So it can dissipate the power. And I can even feel with just one thing, I can feel it's a little warm, right? So that's expected. So what you want to do is you want to, you know, we don't want to have any problems. We don't want to overheat, cause the part to melt, anything like that. So we're going to have heat sinks, and we're going to design it to not be near its maximum. And then the other thing is to keep in mind, because if you kind of mess it, you know, it allows error where you like, you misunderstood what the calculations for the power, and you have so much margin that it's not a problem. Because let's say if you're at a 5-volt supply and you're overloading it and starts bringing the voltage down, that's the other thing that can happen. So what can happen is like you start bringing the voltage down, you bring the voltage down, the current's got to go up, and the current might be limited, and basically start damaging components. That's the type of thing that happens. So now you're sitting there, you're just messing around with projects, and all of a sudden you burnt out parts. You know, you messed up parts because, hey, you dropped the voltage to 2 volt on a 5-volt thing, and there's a bunch of currents, did something in there, and then, you know, you're not sure the part's bad, blah, 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 blah. It just makes your life, you know, a headache. Like, I'm doing this for fun. If I want headaches, I'll just, you know, I just focus on my day job where, you know, we calculate the power of every NAND gate and in a billion NAND gate design. We just calculate the power for everything, and it's a totally different world, you know. But for this stuff, want to make it simple, fun, don't have to mess with that. So that's it for this one. As you can see, I don't have it all figured out, but we'll learn it together. Talk to you later.